So, we were discussing this equation and we found that in the region where rho is extremely large, this differential equation will reduce to that, and that has a solution which is of the form e to the power of minus rho by 2 with a constant here, but that is valid only in the region where rho is very large, and therefore we said okay, we will replace that constant with a function and say that the result is a solution of the equation. So, we want to find capital F in such a fashion that this product actually satisfies that differential equation. So, what I now have to do is I have to take this and put it into the differential equation and to find the equation for capital F. So, let me do that. What I will do is, first of all, I shall take the derivative of S with respect to rho, assuming S is given by this expression. So, what will be the derivative? It is going to be first I will differentiate F, I am going to get dF by d rho e to the power of minus rho by 2 minus, then I will have to differentiate the second term, that is going to give me minus 1 by 2 F of rho e to the power of minus rho by 2. I will need the second derivative, so I am going to have d square S by d rho square. What will that be? Well, you have to take the second derivative of this. Let me very quickly write it. So, differentiating that gives me this, then from here minus half dF by d rho once more, and finally for differentiating this will give me plus 1 by 4 F e to the power of minus rho by 2. So, now it is only a question of just substituting this expression in here and this expression in there, and collect the terms together and get the final equation. Okay. So, maybe what I will do is I will just multiply this term by 2 by rho. Okay, this is this term I shall multiply by 2 by rho. I will put a 2 by rho here. So, naturally I will get a 2 by rho there and a 2 by rho there. So, I can say this result is 1 by rho. And I am going to add this with that and replace this whole thing. Okay, maybe what I should do is I should write on top. Second derivative of F multiplied by e to the power of minus rho by 2. Then here this term and that term are actually identical, so I can just add them up, minus dF by d rho e to the power of minus rho by 2. This term is plus 1 by 4. So, that finishes off this term. Then I have this term. So, that finishes off this term, and finally I have this also to account for. So, let me write that up here. It is fairly simple, lambda by rho minus L into L plus 1 by rho square minus 1 by 4, just wrote this term. S is actually f into e to the power of minus rho by 2. And if I added all these things up, I shall have to get the answer 0. Correct? That is how it is. If I substitute all these things up here, and I again hope there are no mistakes. And with that hope, I am going to remove this, but maybe you should check that I have not made a mistake. Okay, maybe what will I do? Let me just remove this. I hope I have not made any mistakes. Well, the first thing that you will notice is that e to the power of minus rho by 2 is common everywhere. So, we will just remove that, easy for me because I just have to rub off this. I am perfectly allowed to do that, and then I should be able to simplify. Can you just check whether I have done anything problematic here? I suppose not. Okay, so the equation becomes d square f by d rho square, first term, plus I have terms involving df by d rho. There is a 2 by rho coming from here, so this will be here, and there is a minus term which I will put here, so minus 1. Then what are the other terms that I have left? This term lambda by rho, this I have put here. There is another minus 1 by rho times f. So, I can modify this and say lambda minus 1 by rho. So, this also I have accounted for. This I have accounted for, this one I have accounted for. There is a plus 1 by 4 and a minus 1 by 4. So, naturally the 2 will cancel, and I will be left with minus L into L plus 1, which is this term, divided by rho square into f is equal to 0. So, I am fine actually, because I look at the PowerPoint presentation and I see that I have the same equation as in the PowerPoint presentation, and therefore, I have not made any mistakes. Okay. But then this has to be solved subject to one condition. What is the condition? The condition is that when r becomes very large, small r becoming very large. If small r becomes very large, that means you are far away from the nucleus. Then the rho will become very large, and if rho becomes very large, I want this solution to be well behaved, which means that S has to approach 0. S should approach 0 when rho becomes r, or essentially rho becomes infinity. You may say that, well, is it not obvious that there is a c to the power of minus rho by 2? But suppose this f is a function which behaves like e to the power of plus rho, then you will obviously have a problem, and that is actually what happens, right? That is actually what happens. This function f, if it goes to infinity, I mean, we are going to make use of a series expansion for f. We will find that that series actually may not terminate. It may go and contain infinite number of terms, and if it contained infinite number of terms, this f will behave like e to the power of rho. I am not going to prove this, but I am telling you this is the way it is, and so therefore, we have to be very careful. So, now I have to solve this equation, and how do I solve this equation? The procedure is going to be the series expansion. So, what is the series expansion that I am going to adopt? I am going to say that this F may be written as a power series in rho A0 plus rho A1 plus etcetera. But that is not exactly what I will do. I will think of a more general power series, where I will say that okay, it may be of the form rho to the power of s, s is undetermined yet, into A0 plus A1 rho plus A2 rho square plus etcetera. You will agree when I say that this is a little bit more general than what we were doing earlier, because if you put s equal to 0, you will get the original, the earlier kind of things that we were doing. And the reason why we do this is actually, if you look at the potential, you see you have 1 by rho square, you have 1 by rho sittings in different places. So when rho approaches 0, what will happen? These terms you would expect will be perhaps diverging, and to cancel that divergence kind of thing, we include this essentially. Okay, this is the basic reason. But anyway, this is what we will do, and therefore what will happen? I will write this as A0. I can take this inside, rho to the power of s plus A1 rho to the power of s plus 1 plus A2 rho to the power of s plus 2 plus etcetera A nu rho to the power of s plus nu. This is what we will write. And this differential equation itself, what I will do is I will multiply throughout by rho square, so that I do not have any division by rho. And if I multiply throughout by rho square, what will be the result? I will get rho square d square f by d rho square plus, if you multiply this, the answer is going to be 2 minus rho into rho. Or maybe I will write this as 2 rho minus rho square plus lambda minus 1 into rho minus L into L plus 1 into F is equal to 0. So this is the equation that I should now solve. So that means I will need df by d rho first of all, what will that be? Well, you have to go on differentiating this, you will get s into A0 rho to the power of s minus 1 as the first term plus A1, well, s plus 1 into A1 rho to the power of s. I mean, this is simple differentiation. And what will be the general term? You will get s plus nu A nu rho to the power of s plus nu minus 1. Correct? One differentiation I have done. Let me carry out the second differentiation. The second differentiation is going to be fairly simple and straightforward, s into s minus 1 A0, but tedious. that is the second derivative, right. So, but you need see I will need rho square into d square f by du rho square. So, let me straight away multiply by rho square here, and that will you will see that it will remove this minus 2, here it will become plus 1, correct, and here again it will remove this minus 2, that is it. So, rho square into the second derivative will be giving me that. Then I will need this term 2 rho into df by d rho, right. This term 2 rho into df by d rho. So, let me write that 2 rho into df by d rho would be how much? You just have to take this expression which is df by d rho and multiply it by 2 rho. So, I will leave the 2 outside and write this as s into a0 rho to the power of s plus this will give me s plus nu a nu rho to the power of s plus nu plus etc. That will be the general term. Agreed? And all that I have done is I have taken this equation multiplied by 2 rho and wrote it, that is all, nothing more. And then of course, I will have to evaluate this term minus rho square into df by d rho. So, I have df by d rho written here. So, I will just put a minus rho square here. That means, I will have a negative sign sitting outside, and I will have a rho to multiply by rho square. So, this will become s minus 1 plus 2, which actually becomes s plus 2, sorry, s plus 1. Then this will become s plus 2, and this term will become s plus nu plus 1 plus etc. Right. And if this is the way it is, maybe because you see eventually what I will do is I will look for coefficients of s to the power of rho to the power of s plus nu, that is what I am going to do eventually, and then I will say that that coefficient should be equal to 0. So, therefore, maybe what I should do is I should write one more term here which will contain rho to the power of s plus nu, because that is more convenient for me to write it straight away. So, that term will be a rho to the power of s plus nu multiplied by a nu minus 1, right, into s plus nu minus 1. I hope it is clear, because I did not have much space there. That is the term that will contain rho to the power of s plus nu. And then from here I am going to get lambda minus 1 into rho into f, right. Lambda minus 1 into rho into f is what I have to write, and that is going to be equal to how much? It is going to be a0 rho to the power of s plus 1, right. Oh no, lambda minus 1 is there, and then rho into f. So, f is written somewhere, f is written here. So, I will use that, and I will get a0 rho to the power of s plus 1 plus a1 rho to the power of s plus 2 plus a3 rho to the power of s plus 3. Is that correct? I suppose it is, plus etc. I will have here a term rho to the power of s plus nu. What will that be? Is that correct? I know I made a mistake, right? To the power of s, this is a mistake. a2 rho to the power of s plus 3. So, if I wanted to look to write the coefficient of s rho to the power of s plus nu, it is going to be a nu minus 1, correct, plus etc. And the last term is minus L into L plus 1 f is equal to minus L into L plus 1 into A0 plus A1, oh no, that is fairly simple. So, you have to add up all these things and say that the result is equal to 0, that is all. But then you again realize that it is a power series. A power series in rho, you are going to say that it should be identically equal to 0 for all values of rho. And if that is to be satisfied, the coefficient of each power of rho must be equal to 0. So, let us actually look at the coefficient of rho to the power of s. What is the coefficient of rho to the power of s? Just to illustrate, take the coefficient of rho to the power of s, you will see that from here you will have rho to the power of s into s minus 1 into a0, right. And then from here what will you get? 2s a0, right. There is no rho to the power of s in any of these terms, it is only here. And from here what are you going to get? You are not going to get rho to the power of s, because it starts with rho to the power of s plus 1. This also starts with rho to the power of s plus 1, right. What about this one? You do get rho to the power of s here, and that is going to be minus L into L plus 1 into a0, and this must be equal to what? This is the coefficient of rho to the power of s. What is written? I mean, this is the term containing rho to the power of s is shown here, so that is actually the coefficient, and the coefficient has to be equal to 0, correct. So, you look at this equation, what does it tell you? It tells you that s into s minus 1 a0, well a0 you would realize is common. So, I am going to take it out, I am going to get s into s minus 1 plus 2s minus L into L plus 1, a0 is equal to, sorry, a0 I have taken out, that is equal to 0. So, if this is to be satisfied, this in fact is not a recursion relationship, because you see a recursion relationship will determine a0 or maybe a n plus 1 in terms of maybe a n, right, or a nu plus 2 in terms of a nu. So, this is not a recursion relationship, but you realize that this equation definitely should be satisfied, and if this is to be satisfied, again what is the conclusion? You can have a0 equal to 0. We will see that that is not acceptable, we will see that in a minute, and therefore, the only possibility is that your s, see I had not determined s was simply some thing that I had introduced. Your s has to satisfy the condition that s into s minus 1 plus 2s minus L into L plus 1 must be equal to 0. So, let me rewrite that condition. It says that s into s minus 1 plus 2s, but that is nothing but s square plus s, correct, minus L into L plus 1 must be equal to 0, right. So, s has to satisfy this condition. See, s into s minus 1 plus 2s, you expand it and you are going to get s square plus s. Now, this is just a quadratic equation in s, you can solve it, right, because you want to find s which will satisfy this condition, and you will find that there are two solutions. One is actually s is equal to L and the other is actually minus of L plus 1. Maybe you can verify this. I mean, if you say that this is a quadratic equation in S and solve it, you will get two solutions. One is S is equal to L and the other is S is equal to minus L minus 1. And then what will happen? Suppose you look at these solutions, I am going to again claim that this is the one that is acceptable while this is not acceptable. Why do I make that claim? Look at the power series. Your power series actually for f starts with a0 rho to the power of s. If you had rho to the power of L here, remember what is L? L may be 0 or it may be 1 or it may be 2, 3, 4, etc. So then this series, this is very well defined, rho to the power of L. Suppose you are very close to the nucleus where rho is very small, then rho to the power of 0 or rho to the power of 1 or rho to the power of 2, they are all very well behaved functions. On the other hand, if you had s equal to minus L plus 1, what will happen is that this will become a0 rho to the power of minus L plus 1, right, and L is 0 or L is 1 or L is 2. What will happen? If L is 0, you will have rho to the power of minus 1 here. If L is 1, you will have rho to the power of minus 2 and so on, and what will happen when rho becomes very small, that is when you are approaching the nucleus, the solution will actually diverge to infinity, right, because when you are very close to the nucleus, you will have rho to the power of minus 1 or rho to the power of minus 2 or some function of that form, and therefore we rule out this solution, only this is acceptable. Okay. So we have now determined the value of S. S has to be equal to L, and remember L is an integer which may also take the value 0. And then let us look at the recursion relationship that we will get. How will we get the recursion relationship? You have to say that the coefficient of rho to the power of s plus nu must be equal to 0. So, you have to collect together terms which will involve rho to the power of s plus nu. So, let us do that. Well, here again I have to be very careful. From here I will get one term, so that is this term. Here again I will get one term s plus nu into a nu, but there is a 2 sitting outside. So, I have to remember that. So, I have taken this term, I have taken this term into account. Now, I have to take this term into account. How, what is that? S plus nu minus 1. Is that okay? This one is minus, correct? Thank you. I mean, otherwise I would have been in difficulty. This is a minus sign. Then from here I am going to get plus lambda minus 1. What is the general term? A nu minus 1. And from the last one, minus L into L plus 1 a nu, what is the term? Yeah, I think that is it, minus L into L plus 1 into a nu, and that must be equal to 0. Correct. So, I will rearrange and write it as a recursion relationship, which says that a nu must be expressible in terms of a nu minus 1. Now, here things are a little bit different. Earlier you see it was always a nu plus 2 is expressed in terms of a nu, that is how it was, but in this case a nu plus 1 is expressed in terms of a nu, or a nu is expressed in terms of a nu minus 1. Okay. So, what is the expression? The expression is actually well, I suppose I can just write this, I suppose this is the recursion relation. All that I have done is I have taken this term and that term to the right hand side, these two terms, because they are dependent upon a nu minus 1. So, I have taken to the right hand side and rearranged, and I will get this equation. Well, what I will do is, normally you see we express I mean in the previous cases we had expressed a nu plus 2 in terms of a nu. So, we will do a similar thing here, we will express a nu plus 1 in terms of a nu. What is the relation? Right, all that you need to do is wherever nu is occurring, you just replace it with nu plus 1. Before I do that, actually you will see that this minus 1 and that plus 1 I could have cancelled. So, with that let me just replace nu with nu plus 1. I am going to get s plus nu plus 1 into, no, there is no, into s plus nu plus 1 minus lambda divided by s plus nu plus 1 into s plus nu plus 2 times s plus nu plus 1 minus L into L plus 1. This is what will happen. So, a nu plus 1 is determined in terms of a nu, correct, and now you will realize why a 0 cannot be 0, because if a 0 is 0, this recursion relationship will imply that a 1 must be 0, and if a 1 is 0, then a 2 will be 0, then a 3 will be 0. So, the entire power series will become 0, and that is not acceptable, because the wave function will identically vanish. So, you cannot have a 0 equal to 0, which is what I had said earlier. Okay. And now again you have the problem. What is the problem? The problem is that the series should not go to infinity, because if it went to infinity, your wave function will not be acceptable. So, for some value of nu, what should happen is that a nu plus 1 must be equal to 0 for some value of nu, maybe nu is equal to 4. So, a 4 is non-zero, but a 5 has to be 0. So, what is the way out? The way out is to say that lambda must be equal to, right, if lambda is equal to s plus nu plus 1, there is absolutely no problem for some nu. Okay. So, what is going to happen is lambda must be equal to s plus nu plus 1, and what are the values that nu can take? You can have a solution where you put nu equal to 0. You say that lambda is equal to s plus nu plus 1, but with nu equal to 0. So, it is lambda is just s plus 1, that is one possibility. The next possibility is lambda is equal to S plus, you put nu equal to 1, S plus 2, then S plus 3, S plus 4, etc. But what is S? We have already found S. S is actually equal to L. It is equal to our quantum number L. So, therefore, I will now replace this S with L, right. And so, we find that lambda must be equal to L plus nu plus 1. What are the values that you can assign to nu? Nu may be taking the value 0, 1, 2, 3, etc. Any one of these values is possible, you are going to get an acceptable solution. Now, you see this combination is difficult to write. So, what I will do is I will introduce a number which I will refer to as n. What is n? N is equal to L plus nu plus 1. So, then what are the different values for n that you may assign? You may say, well, n can take the values, well, nu can have the minimum value 0. So, if minimum value of nu equal to 0 means n may take the value L plus 1, right. So, L plus 2 plus etc. correct. Or you can say that this number n, if I introduce n minus 1, what is the definition of n? N is equal to L plus nu plus 1, which implies that n minus 1 is equal to L plus nu, and nu can take the values of 0, 1, 2, 3, etc. So, therefore, you have the condition that n minus 1 has to be greater than or equal to L, right, if correct, because n minus 1 is equal to L plus nu, and nu can take the value 0, 1, 2, 3, etc. and this n is actually nothing but your principal quantum number. That is what you will find, the number that we have introduced is actually the principal quantum number. But what have we found? We found that lambda must be equal to n. What is the minimum possible value of n? It is 1 obviously, right, because L may be 0, nu also may be 0, but then you have a 1 here. So, minimum possible value is 1, next possible value is 2, next possible value is 3, and so on. And further we found that lambda is equal to n. We had a definition of lambda, unfortunately that has been rubbed off. So, I will have to depend upon your notes or my notes to write the value of lambda. Lambda was defined to be mu e square divided by 4 pi epsilon 0. What else did we have? H cross square. Anything more? Alpha, right? So, this was the definition of lambda, and lambda we now say, okay, lambda has the value, it is equal to n, where n is an integer which may take the value 1, 2, 3, 4, etc. And therefore, what will happen? You are led to the conclusion that alpha must be equal to mu e square divided by, you take alpha here, n on to the other side, by n h cross square 4 pi epsilon 0. Right, alpha must be equal to that, and now alpha is related to the energy. What is the relationship? Alpha square must be equal to that. So, therefore, what I will do is I will take this expression for alpha and put it there and say that, okay, I do not have solution for arbitrary values of alpha, but only for these values of alpha. I have solution only for these values of alpha, but alpha is related to the energy. So, therefore, what is the conclusion? The conclusion is that only for certain values of energy would I get acceptable solutions, and what are those values of E? How will I find that? Instead of this alpha, I will put that expression, and solve for E. Okay. What is the expression that you will get? So, you are going to get this equal to mu E square divided by n h cross square 4 pi epsilon 0. This is just alpha, you have to take the square and say that that square is equal to that much, and then solve for E. Okay, I will write the answer in the next lecture, but you will see that that E that you obtain is nothing but the expression that Bohr had obtained. The expression that you will get is just the expression that Bohr had obtained in his theory, which assumed that there were only certain orbits that were allowed. So, exactly the same result you will get by solving the Schrodinger equation. Okay. So, we will continue in the afternoon. So, thank you for listening.